Okay, so before we start looking at the crazy log equations, I wanted to make sure to touch on the writing assignment, particularly question 4, because question 4 actually was a question on our final exam like a year and a half ago, 2 years ago. And some students really struggled with the problem because it's giving us a lot of information and they understood the information, but they didn't understand how to turn that information into an exponential function. So the first thing is when they tell us that we're going to drop by the same percentage, that means we have an exponential function. Now, since they said drop, this means it's an exponential decay function. So we are expecting our b value to be less than 1, but still positive. So what a lot of people think when they first look at this, so we've got like some information associated together. So I know that my car was valued at 38K in the year 2007. And then it dropped to 11,000 in 2013. And then our question is, how much is it going to be worth in 2017? So a kind of like rough idea is we're losing 27,000 in the first 6 years. So if we were dropping by the same amount every year, we would take that 27,000 divided by 6. That would be the yearly amount of loss. And then we'd just do that subtraction 4 more times to get from 2013 to 2017. But that's if it was a linear progression of loss. An exponential percentage is going to work differently. So instead of the difference, we actually have to look at the ratio, at the proportion. And we're going to see that show up in our exponential formula. But to use our exponential formula the way we first learned about it, I need ordered pairs. I need XY points. So I've got two pieces of data here. I've got the car value and I've got the year associated with it. So I've got an input and an output, but the question is which one's which? So when we talk about exponential functions, growth and decay, what is usually our input or what is usually our x-axis variable? Time. So very often it's like number of days for a bacteria culture to grow or years for a population of animals or whatever. Or sometimes it's like a really ridiculous number of years when you're looking at carbon dating. So our time is our input variable. So our x is measured in years, but I really don't want to put the number 2007 in my function. If I do that, my a and my b values are going to be really disgusting looking. So instead, I'm going to redefine my frame of reference. So I'm going to take my starting year, my earliest year, 2007, and I'm going to call that my starting value. So if X is the number of years since 2007, then 2007 is 0 years since 2007. So that is an X value of 0. For 2013, the X value is going to be 6. For 2017, the X value 17 is 10 years after 2007. So we have an X value of 10. So now that I have those X values, the monetary values I'm getting out, those are just going to be the numbers, the output numbers. So I now have two ordered pairs. So I had some people on the test couldn't figure out how to get from the sentences to those ordered pairs, and then they struggled with the whole problem. Even though they knew how to find the function from the points, they couldn't get from the words to the points. So we fixed out that on the test, like we give you the words, but then we say, which gives a starting point of, and we'll define the starting point. And then this other piece of information, which gives this secondary point. So we are going to explicitly tell you the points and ask for the function, but then we're also going to ask the follow-up question, like what's going to happen in the future if this trend continues? So now that we have the 2 points, our exponential function is f of x equals a times b to the x. So we're going to use our 2 points to solve for a and b. So I'm just going to plug in my x value is 0. So I have a times b to the 0. And then my y value, my function value is 38,000. So I put 38,000 on the left. And then my other one, I end up with 11,000 equals a times b to the 6th. So 38,000 equals a times b to the 0. But what is b to the 0 power? 1. So a times 1, it's just a. So by redefining our starting year to be 0, that turns the starting value into our a value. Now that I know that a value, I'm going to bring that over to my other function. And now I've just got an equation in terms of b. So now I can solve for b. So first step, since that's 38,000 times b to the 6th, I'm going to divide by 38,000 because I want to keep the b. So I now have b to the 6th equals 11 over 38. All right, now we got to get b by itself. So I got to get rid of that 6. So what do I do to get rid of that 6th power? Say it again. Yep, root 6, that's one way to write it. But my only hesitation with root 6 is then when I go to my calculator, do I see a root 6 button? Not usually. Some calculators will have an X root button and you can type the 6, but even using that button gets really weird because you're like, do I put the 6 first and then hit the button? And that is usually the syntax, but it's still confusing to me. So log base 6 would bring the 6 down on the line in front of it, but then we'd have a log base 6 attached to the b, and then I'd have to get rid of that again. So it'll get the 6 out of there, but it's not leaving me just b by itself. Like that's what I want the next line to be, is just b to the first power. So I'm going to tell y'all a cheesy joke off here to the side. So when I was first learning exponent rules, I struggled with quite a number of these rules. Especially the first and the third one. I really struggled remembering the difference between them. But I did realize after a while that the first one, x squared times x to the third, that is 2x is being multiplied, and then 3 more x is being multiplied. So altogether, it's 5x is being multiplied. So we can just add the exponents. But then I came up with like a story to kind of remind me of this. So these guys are like two apartments or dorm rooms next door to each other. You see your next door neighbor every once in a while. It's a pretty cool relationship, so it's positive. So those exponents can add if we're just like, how many people are living there? Upstairs, downstairs neighbors, though, not a good relationship. Upstairs neighbors have a large dog. Throw the ball, whack, thump, 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 thump. And then again, and again, and again. I felt very bad for the dog. Downstairs neighbors smoke so much pot, it leaks into your apartment. And I am normally a very live and let live, like whatever, but my roommate at the time was actually allergic to THC and would get migraines. We also had like over 10-foot ceilings. Do you know how much you have to smoke to fill a 10-foot ceiling apartment? Like it was ridiculous. So upstairs, downstairs neighbors do not get along. This is a negative relationship. So the powers subtract. But then we only have one base and we've got two exponents. They're much closer together. We got the 2 getting all close to the 4. The only thing in between them is the condom of mathematics. So what are the two numbers going to do? Multiply. Because there's a condom in between them, so they're going to multiply. There's my bad joke. The big thing was I would struggle between the first one and the third one. So I finally realized like if there's a whole x in between, they're not close enough to multiply. If there's only a parenthesis in between, they're close enough to multiply. So now all that being said, when I have my b to the 6th back over here, and I want to turn it into b to the 1st power, like I could multiply by, or I could divide by b to the 5th, and then b to the 6th divided by b to the 5th would be a b to the 1st. But then the other side would now have b to the 5th. So I'm not getting b by itself if I divide. Same thing if I multiply by something. So the only thing I can do that'll leave me with the singular base without extra b's on the other side is to raise it to an exponent. So the exponent we want to put here is the number that we do 6 times this number, and it'll equal 1. Yep, 1/6. 6 times 1/6 is 1. So 1/6 is the power that undoes the 6th power. So if I put that 1/6 power on one side, I have to do the same thing on the other side. Now I put the little caret there just to remind myself that this is an exponent, that it's not a fraction times a fraction. Because sometimes when you're looking at your work later, and based on how bad your handwriting is and whether you decided to start writing diagonally, it can look like a product instead of exponents. So putting that little symbolic notation can help. Now, when we type this in on the calculator, we do need parentheses everywhere. So we have 11 over 38 in parentheses, and then our x to the y button, and then that 1 divided by 6 is also in parentheses. So our b value is 0.81333, and then it goes 26026. So it is some weird decimal. There is no pretty fraction answer for this. I raised it to the power of 1/6. So that's why I put this little like up arrow caret symbol. That's at least like on my calculator, when I hit the X to the Y button, that's notationally what it does. just because my phone calculator can't actually do superscripts. On other calculators, it'll be like 1/6 will be up higher and a little smaller, so it looks like a power. So now I have my A and my B value. I can write my function formula. My A value is 38,000. And then my B value is annoying decimal raised to the X power. So we did a whole lot of work. We got our function formula, and that is most of the points on the final for this question. But then the follow-up question was, what's it going to be worth in 2017? And we decided 2017 was going to be X equals 10. So this is really asking us, what's the function evaluated at 10? So f of 10 is 38,000 times ugly decimal to the 10th power. Now, since I still have ugly decimal on my calculator, I'm just going to hit my xy to the 10th and then multiply that result by 38,000. And I get 4,813.5491. Now, what is this number representing? Yep, so this is a money number. So we could round it to cents. We could even round it to dollars if we want. So 4813.55. So a little more than 4,800. So when I look at my change in values, I lost 27,000 over the first 6 years, but I only lost about 6,200 over the next 4 years. So it's definitely not a linear change. It's a percentage change. So we lose more in the earlier years than we do later on.
You can't do it that method. It's like y equals p times r minus 1. That would work for this.
1 minus r. Yes, you could do it that way. You're getting the percentage change number. So 1 minus r is equal to the b value. But it does still work. The number looks a little bit different, but the end result formula, if you do 1 minus the r number you got, it would be the 0.81333. The final is cumulative, but there is going to be a focus on the last material. So there are 5 questions from the last section out of the 17 questions on the final. But some of those questions on the final are relatively short and multiple choice. Some of them are going to be a little bit longer. When is our final? Let's see. So I don't remember any of my courses individually because I just know I have a final on Thursday, Friday, Monday, and Tuesday. Let's see. Ours is, I believe, the Thursday. Yeah. So Thursday, May 7th at 11 a.m. So a week from Thursday. So 11 a.m. to 12:50. Now, if that time is going to be a problem, I have other finals. You're more than welcome to come take your exam in one of my other classes because I'll probably have a few empty seats. But just email me and let me know that's what you want to do. Now, the other part of the writing assignment I wanted to touch on is question 7. Some of them are a little weird. Overall, the question format is pretty straightforward, but the first couple ones sometimes throw people for a loop. So this question is asking us to figure out what the value of x is. So there's actually a couple of ways to solve this, but usually what I do is I change this into exponential form, and then I kind of figure my way through what the power has to be to make it make sense. So log base 121 of 11, if I want to get rid of the log, I have to use the 121 exponential base. So I'm going to apply the 121 exponential to both sides of the function. Now the 121 to the log base 21 cancels each other out. So we just have 11 equals 121 to the x power. Now here I got to think about how do 11 and 121 relate? So 11 squared is 121. But I want to know, how do I write 11 in terms of 121? So we're going to do something a little weird, but I'm starting with a known fact, a true statement. I'm just going to do some algebraic manipulation to it. So that 11 squared, if I want to get rid of the square, I could square root, but I'm going to write the square root instead as the 1/2 power. So this is telling me the fact that 11 is the same as 121 to the 1/2 power. So I'm going to trade that out. But now I can see my 121 to the x equals 121 to the 1/2. So that means x better be 1/2. So that's one way to think through solving this one. There's a couple of ways to do it. Now our b there, that 7th root of 4. The 7th root is just the power that cancels out the 7th power, which we kind of reasoned through earlier. The 6th power got canceled by the 1/6 power, so the 7th power gets canceled by the 1/7 power. So the 7th root of 4 can be rewritten as 4 to the 1/7. So I'm not working the whole problem, but you can use that as the key to figure out what the solution is. And then we get C here. So log base 3 of -9 equals t. Now you can, using the change of base formula, you can type these on the calculator. Like we could have typed natural log of 11 divided by natural log of 121, and the calculator would have spit out 1/2 for us. And that's a totally valid way to solve the log equation. This one, though, if we try to type it on the calculator spits back nonsense. So let's dig into it a little more and think about what it means. So log base 3, I can cancel out with my 3 exponential. So when I rewrite this equation, I have -9 equals 3 to the t. So when I think about 3 to the t, when I plug in 0, 3 to the 0 is 1. When I plug in 1, I get 3. When I plug in 2, I get 9. Then if I move the other direction, if I plug in -1, 3 to the -1 is 1/3. 3 to the -2 is 1/9. So I get that curve. It goes through the point 0, 1, shoots off to infinity on one side, and then starts hugging the y-axis on the other. Now our equation is asking, where does that graph equal -9? Never. There is never a spot where our exponential graph is going to get down into the negative numbers. All of our output values for an exponential function are positive. So this never happens. So this is a false statement. If I typed it on the calculator, I would get a domain error. So that means there is no real solution to this equation. There might be some imaginary number, but I don't have to figure that out.
No real solution and does not exist. Are those like two interchangeable words?
We usually only use them in particular contexts. So we say there is no solution when we had an equation with a variable in it. Normally having an equation with one variable is enough to solve for the variable. But if we do a bunch of math and then we get to the realization that there is no solution to this equation, like that's when we say no solution. But it's not that the equation does not exist. Like we wrote the equation, it exists. It just doesn't have a real solution. Whereas other times, like in calculus, when we say does not exist, it's the definition required for the thing is not met. So we've got like things where we're like the left side and the right side have to do the same thing. And if the left and the right side are doing different things, we say, oh, this thing doesn't exist because the left and the right are not agreeing. So the left and the right exist and have values, but because the values are not the same, the overall thing we say does not exist.
Thank you.
All right, now did y'all have any other questions on the writing assignment that's due today? Any other ones that you wanted me to talk about, comment on? Now for next week, there is 2 writing assignments due. One of them is solving exponential and log equations. And then the other one is your final semester reflection. If you need more time to turn in the final semester reflection, that's fine. You could technically even turn it in after the final. I wouldn't wait too long though, because sometimes I actually manage to get grades in quickly, but there is some extra time in there. All right, so let's flip back and look back at our logarithm equations then. So when we're solving log equations, The way the book presents it is they say, use the definition of a logarithm to solve log equations. So for any algebraic expression S and real numbers B and C, I can take a log equation and then change its form and get the exponential equation over here. So the book presents this as a magically the left equation turns into the right equation. And they're not wrong, but I really hate explanations that depend on stuff just magically moving and you have to remember where everything goes. Because if you're dyslexic, this is an absolute recipe for disaster. So this is why when I cover this, I solve the equation, I transform the equation using inverse operations, not the book's magical, oh, look, here's the new form. But if you already know how to do it that way, you're comfortable doing it that way, I'll still grade it. It's not wrong. I get more value and more meaning from using the inverse. So let's write down our equation. Log base x of 27 divided by 125 is apparently equal to -3. So I have an equation. There's an x in it. There's no other variables. So I should be able to solve for x's value. Now, my logarithm is my outermost operation here. So that's the thing I want to get rid of. So I have log base x. So to cancel out log base x, I use the exponential of base x. So x to the log base x cancels out. So I just have 27 over 125. And this is now equal to x to the -3rd power. All right, so that format's a little more familiar. My x is the base now instead of inside the log base. But now I've got the -3rd power that I want to get rid of. So I got to raise this to an exponent. So what exponent do I need? So I do -3 times this new exponent number will equal 1. Yep, -1/3. So I need it to be negative, so that way negative times negative becomes positive, and then the 3 gets canceled by the 1/3. So that's what we're going to type in our calculator. So we got 27 over 125 in parentheses, raised to the -1 divided by 3, also in parentheses. And my calculator spits out 1.6 repeating. So that's 1 2/3, which as a fraction is 5/3. So we end up with very excited Kermit the Frog. We just used our basic inverse operation on both sides, and then just used our normal equation solving procedures to finish it out. So all we're doing here is we're solving equations just like we've been doing since you started learning algebra. We just now have some extra tools we can apply to both sides of the equation. All right, so our next little equation here, 2 natural log x plus 3 equals 7. All right, so what is the first thing we want to do to this equation? So we want to get the x by itself. So if I was going to get rid of that 2, what would I do to get rid of it? All right, now when I divide both sides by 2, I have to divide both entire sides by 2. So it would be this entire side by 2 and this entire side by 2. So then I would have natural log of x plus 3 halves equals 7 halves. But I can do that as my first step if I want. All right, now what else do I need to get rid of? The 3 halves. So how would I get rid of adding 3 halves? Yep. So we subtract 3 halves from both sides. And 7 halves minus 3 halves ends up being 4 halves, which is 2. Now I also could have minused the 3 first. I would have had 4 on the other side, and then 4 divided by 2 is 2. So you can do those orders in either way. But now I've got that natural log x by itself. So now what gets rid of natural log? Yep, e. So if you're looking at the natural log and you're like, I don't remember what we're supposed to use. So we've got 2 logarithms that have invisible bases. So if I just write log, what's the invisible number? 10. When I write ln, what's my invisible number? Yep. So if this is log base e, then I need the e exponential to undo it. So now my e to the ln cancels out, so I just have x. And then e to the second power, I'm just going to type e to the second power, which that is apparently 7.38906. So if I plug in e squared into my original equation, it'll make a true statement. I'll end up eventually with 7 equals 7. So questions on how this one shook out? All right, now our next one's a little more interesting. We've still got some addition, subtraction, some multiplication, and a log in there, but the order they're all thrown in there is a little bit different. So log base 2 of 1 minus 2x is equal to 3. So my outermost operation on this equation is the logarithm. So that's the first thing I need to get rid of. So I'm going to apply the 2 exponential on both sides. So I have 1 minus 2x equals 2 to the third power is 8. 2 times 2 times 2. And now I'm just solving an equation like normal, so I'll minus the 1 over. I have negative 2x equals 7. And I get x equals negative 7 halves. And there should be a tiny bit of hesitation here. So we got a negative number, but we started with a log equation. Can I take the log of a negative number? So if we're not sure, like literally just try it on your calculator, see what your calculator does. So like ln of negative 2. Mine says cannot show undefined result. And it turns the whole thing red. So I can't take the log of a negative number. So getting a negative solution for a log equation should have a moment of like, is this really the solution? Did I make a mistake somewhere? So what we want to consider is logarithms. When we have a log equation, there is actually an implicit definition of a domain restriction. So the 1 minus 2x in there must always be greater than 0. Now, if I'm going to solve this little inequality to get my easier to read domain restriction, I end up with 1 is greater than 2x. And then I divide both sides by 2. So we have 1/2 is greater than x, or I can mirror image that and get x is less than 1/2. So any number smaller than 1/2 is okay for the domain of this logarithm. So is negative 7 halves less than 1/2? Yep. So negative 7 halves is a viable number for the domain. So that's okay as a solution. And because our formula was 1 minus 2x, like that minus in there with the x after the minus means all of our negative numbers will make that inside positive. And our positive numbers are actually what gets left out. Like I can't put x equals 1 in that equation. I'll end up with log base 2 of negative 1, which doesn't exist. So sometimes we'll have a log equation that we do all the steps and we solve and we get a solution. And it turns out that the solution isn't within the domain restriction. So we might actually throw out a potential solution and we may end up with a log equation that has no real solution. Now, usually if there's only a single x, there's a solution. But the potential exists that there may not be one, or especially when we have a log equation that has more than one solution, very often one of the solutions does not work and we throw it out. All right, now our next equation is going to be a little more explicit about this. So this is the type of equation that I put on the final for the logarithm equation. Now, for all the log equations that we're solving, this one is absolutely the worst one. But it is still solvable. It's going to, well, we'll see what happens. But the first thing to consider is that both of these logarithms set up a domain restriction. So the x plus 6 and the x plus 2, both of those have to be greater than 0. So x plus 6 is greater than 0 when x is greater than -6. X plus 2 is greater than 0 when x is greater than -2. So those statements overlap. So as long as I stick with the more restrictive one, which is x is greater than -2, all the numbers greater than -2 are also greater than -6. So that is our domain restriction. So our solutions to this equation must be greater than -2. So now that we know the domain restriction, now we're actually going to solve that equation. So when I have log base 5 of a thing plus log base 5 of a thing, I need to combine these logarithms because my exponential function only works if I do it to both entire sides of the equation. The exponential function will only cancel out the logarithm if it's a single logarithmic expression. So I need to do my conversion from the plus into what it would be instead. So our log property, when I have two logarithms that are being added, I can merge these together inside one logarithm as a product. Now I have a single logarithmic expression. Now I can get rid of the log base 5. So I use that 5 exponential to both entire sides. So I will have x plus 6 times x plus 2 is equal to 5 to the first power, which is just 5. So now I have a quadratic equation to solve. So I need to unfoil the x plus 6 times x plus 2. So I'm going to get x squared plus 2x plus 6x is plus 8x plus 6 times 2 is 12. And this is equal to 5. To solve a quadratic, I need it to be equal to 0. So I'm going to minus my 5. So we end up with x squared plus 8x plus 7 is equal to 0. Now there's not a lot of choices here, and this does factor. It will factor on the final. So we have x and x, and then the only way to get 7 is 1 and 7, and everything's positive, so it's x plus 1 and x plus 7. So now when I set each of those factors equal to 0, x plus 1 equals 0 gives us x equals -1. X plus 7 equals 0 gives us x equals -7. So -1 is greater than -2. So that's a good solution. -7 is not greater than -2. So we cannot use -7 as a solution to the original equation. So our only solution here is -1 because of our domain restriction. So even though the quadratic had two solutions, only one of them works in the original equation. So when I say both of those statements are true, let me grab my annotate. So when x is greater than -6, that's all the numbers to the right of -6. When I say x is greater than -2, that's all the numbers to the right of -2. So the area where they're both true is just all the numbers to the right of -2. The A answer choice, that inequality symbol is backwards. So that's why we don't pick that answer. So we are saying both of them are true. It's just x is greater than -2 is the shorthand way of where both of those are true. All right, and then we got a weird word problem. So a mutant blob of cheese left in the fridge too long starts to grow uncontrollably. According to the law of uninhibited dairy expansion, its growth is modeled by the following function, where C of t is the mass of cheese blobs in grams, t is the number of days since the fridge rebellion began. We need to stop or admire the cheese blob by answering some questions. So first, what is the initial amount of the cheese blob? So what did we start with? Yep. Our number in front of the exponential, the a value, is always our initial starting value. Another way to figure that out is initial means when time is 0. If I plug in 0 for t, e to the 0 is 1, so we get 100. So 100 grams is what we start with. Now they ask, what is the rate the cheese is expanding? So the rate, it turns out, is that decimal up there, I believe. So that was just our e to the percentage value. Now, what is the population after 5 days? So after 5 days, that is asking us to figure out C of 5. So we have 100 times E to the 0.045 times 5. We end up with 125, and they said 2 decimal places, so 125.2322. So 125.23. So now the question is, how long until it reaches 140 grams and breaks the fridge door? So 140 grams is an output number. So they're asking, when will the function equal 140 grams? So we have 140 equals 100 e to the 0.045 t. So we're going to start solving by dividing by 100. So I end up with 1.4 equals e to the 0.045 t. Now to get rid of our e, we use our natural log. So the natural log of 1.4 equals 0.045 t. And now we divide by the 0.045. All right, so natural log 1.4, close parentheses, divided by 0.045. So 7.477. They said 2 decimal places, so 7.48. And that is days. All right, so questions on how this wacky word problem shook out. So that's the end of all of our amplify activities. Now in web work, way at the end here, it says practice final exam. There are 20 questions here. Now there's only going to be 17 questions on the final, so there's a few problems that are kind of duplicates, but this is a really good match for what's going to be on the final. Now, hopefully you remember this ridiculous question. So you're not going to have all three functions on the exam. You're just going to have one of them on the exam. And you're finding the domain of that function. All right, so we put one of these crazy Franken-function trig equations with a A, a B, a C, and a D value. All you have to do on the test is the amplitude, the period, the midline, and the phase shift. You're not going to have to sketch the graph. So we still got to remember our information and remember how to interpret it from the equation, but you're not going to have to sketch a graph, like figure out the start and the ending values. Just give me the rough, like what the transformations do. You don't even have to do the max and the min on the exam. All right, we've got find an inverse of a rational. We've got a equation that has a quadratic in it. A law of cosines question. A polar coordinates question. Given two gross numbers, find the exponential formula. We have this log graphing one. The reason I put this on here is because we'll have a question that just asks, what's the domain of the function? So you're not going to have to produce the graph, but this is the only question I had that asked about the domain of a logarithm function. So that's why this question is in here. You won't have to do all of it, but you will have to do the domain. We got a log properties, another log properties, exponential equation to solve, and then two logarithmic equations to solve. So is there anything in particular you want to see gone over today? All right. Then what I would suggest is dig into the practice final exam, try some of them out, see what you remember, and then have some questions that you'd like to look at for our class on our next class. So that way I know which ones you guys want to focus on first. We should be able to get through most of them between the two classes we have.